first one, it has no ancillaries. The second one, its implementation will keep the locality of the Hamiltonian. And also it has a very unique feature called commutative scaling. So basically it says like the Trotter error can be expressed by the commutators of the Hamiltonian components. So let me take the 1D meaningless layer, like the Hamiltonian as an example. So in this case, suppose you calculate this kind of the commutator value, you will find that most of the commutators will be cancelled out due to the locality. So this will promise us that the Trotter error will be quite small with respect to the system size. So this will give us like a very good system size dependence. So the major downside, as mentioned by Jackal several minutes ago, is like the limited accuracy dependence. So which limits us like for some application for higher precision quantum simulation. So instead of like decompose the operator by the product of the operators, you can also consider to decompose the operator by the summation of the unitaries. And for a given operator V, we can define the LCU formula for this operator by a summation of the elementary unitaries with amplitude pi and some normalization factor mu. And I think this part has already been introduced by Dong before. So to realize this kind of LCU is a little bit trickier than Trotter. So what you do usually is like you introduce a large ancilla. You first embed this amplitude into this ancilla, and you do some so-called selective gate to implement this BI coherently. And then you unprepare the ancilla state. So if you measure the ancilla and you get a zero outcome, and in this case, you will effectively like implement the V operator on the system. But the probability to get this zero outcome is related to the normalization factor I mentioned here. It's like a 1 mu squared. But successfully, we have some like amplitude amplification method to like amplify this amplitude probability to almost 1, just by some like a Gross's method. And so how to construct the LCU formula for the short-term illusion. So there are several ways, there are many ways to do it. So like here I just mentioned the very simple one proposed by Barry in this PR paper. And the idea is try to decompose this short-term illusion by Telluride expansion, and then you will get a linear combination of the Pauli operators. In practice, to avoid like the infinite gate complexity in the worst case, so usually people do is to do the truncation. And this will introduce a small simulation error. But so what we know is like the Telluride expansion is a very good expansion. It will promise us like the truncation. So the tail of this truncation will be very small. It will be exponentially suppressed. So basically this will promise us to have like a high precision type of like a Hamiltonian simulation. So I just mentioned like Trotter and LCU. Both of them have their own features. But the natural idea will be like, why not just combine them together? Is there any way like to combine them together, like so that we can enjoy both of their advantage together? And also there are many studies about how to combine Trotter and LCU together. So today we mainly focus on a simple idea similar to like error mitigation. So the idea is like during each segment, you first do some Trotter. And then you use some like circuit to compensate the Trotter errors. Just as I mentioned, like the Trotter. So what we need to do is like we need to find an LCU formula for this type of like Trotter errors. So if you do a naive like Telluride expansion, this already gives you like a very complicated like LCU formula. Definitely you can do it by block encoding and application implication, but this will be like far beyond our current research, current reach of near-term quantum computer. So what we do instead is to consider some like random sampling idea. So I think like yesterday, this example gives a very nice talk about like how random sampling can be used to like simplify the quantum circuit, also like improve the quantum algorithms. And I will just briefly mention how we can use it as a random sampling. So the idea is quite simple. So basically, formally we take this V as a linear combination of unitary as a kind of coherent superposition of the elementary unitaries. So now we think this we can treat this LC formula as a kind of random sampling of the VI based on the importance of PI. So suppose we want to estimate some like target state below V dagger, so the rho is the initial state. So what we do is like we expand the V and V dagger by some linear combination of unitary operations, and we then embed this kind of estimation operation into the Hutton test, like a type of circuit. So basically, we change the V, some of the VI and VG in each one, and by using some estimation operator, so this kind of measurement can provide a pretty good unbiased estimation of the final properties of the V dagger and this target state. The caveat is that we cannot implement the unitary. We can only estimate the properties, but this is quite enough. Like we can use it for like estimate the ground state energy, estimate like ground state properties, and also we can use it to simulate all the correlated some observables. And so in our case, actually we can further simplify the circuit. Notice that like the Trotter formula itself is like a fixed. We don't need to sample this Trotter formula. So in this case, we can simplify this whole Hutton circuit like into this kind of circuit. Basically, we first do a deterministic Trotter without any control, and then we do some like a sampling based on some LC formula to sample some Pauli strings. This Pauli strings is based on the LC formula I just mentioned before. And for this form, with this like a Pauli string, you use a single ancilla to do the Trotter error compensation. And due to the last time limitation, I'm not going to tell you the details of like how we construct this LC formula. And if you're interested, you can discuss with me later. And so we may consider two ways to construct like the LC formula. So one way we call the pair series formula. So in this case, we don't consider the commutator structure of the Trotter error. But this kind of expansion admits a very simple random sampling, same as QG. And in this case, we have like in the other LC extension, we consider the commutator form of the Trotter error. This will be complicated, sample, but still we can use it to improve the system size dependence. So here I'll show you like the gate complexity of our methods comparing to with specific different parameters. So we mainly consider three settings. So in the first setting, we don't introduce the Trotter formula. So in this case, we can still do the pair series expansion. So this kind of algorithm is quite similar to the one mentioned by like Compo yesterday. And we find because this is a pure random sampling algorithm without any Trotter formula, we can make it like an L independent. L is the sparse of the Hamiltonian. So basically, it's very suitable for some quantum chemistry application. In the second and third setting, we consider to introduce some Trotter formulas. And this will, by introducing Trotter formulas, we are able to like improve the time dependence to almost linear, and we also have a quadratic improvement compared to the bare usage of the case of the Trotter. And if we use like pair series sampling, this kind of method, you can get the high precision like log to log by through. But for the messy complicated extension, we're not able to achieve it. But we can achieve like a better dependence than Trotter, and also we can achieve nearly optimal computer scaling. Okay, and to demonstrate the practicality of our methods, we also do some numerical estimation of the gate counts. And we consider many two scenarios. In the first scenario, we consider so-called L-sparse Hamiltonian, where we assume that like the commutator information it cannot be used like, to improve the Trotter errors. It's somehow the worst case scenario. So in this case, the formal best protocol is Trotter protocol is to use the fourth-order Trotter with random commutation, and we just try to count the gate count of our Trotter LC protocol, and you can see like this gate count can be improved by a lot. And for the zeroth order, like no Trotter type of like random sampling, you will have a very small overhead, but the time dependence is not good. But for the second order or fourth order Trotter, you can have a great time dependence. So this will be suitable for long time dynamic simulation. And we also consider the Hamiltonian with nearly stable coupling. So in this case, like the computed information will help us to like improve the to reduce error, reduce the error. And the formal best result is force order Trotter in this like paper. And we find that using our nested computed extension, we are able to reduce the gate count. And also for fixed gate count, we can achieve a much higher accuracy. To summarize, basically we studied the idea to compose floating LCU together using this kind of like a combination method. And this will give us like some promise that we can enjoy partially both of their techniques based on the differential use. And our study also shows the power of the random sampling. And also we hope that our research can inspire new research on how to counter that different outcomes together. That's all my talk. Thank you.
Thanks, Pei. We have some time for questions. Okay, maybe I can start with the one. So there's another method called a multi-product formula, which also tries to combine the advantage of the economy scale of the Trotter formula and the post-Trotter formula. So how would you like to compare your method with multi-product formula?
It's good. My action is okay. So really, there's a recently also there work by the ASS group. They also show that you can use multi-product formula for that. So in this case, so basically, what the advantage of our optimal comparison is we can improve the time dependence, and also random sampling. Well, the design of the LCU formula will quite complicated from my perspective, and also they have to do the control for the type of gates. So you have to do the control gate. I think this will be quite. So from this perspective, I think our method will be
great. Thank you.
So if you use your method to compute the observable expectation value at a certain time t, how will it compare with the previous talk?
So in our case, we don't consider the Gitman limits. So still for us, we are similar to the same ID sampling case. So our observable accuracy should be just a sample complexity should be 1 over epsilon squared. So we don't consider to improve this to a Gitman limit. So I guess the performance work they use some extrapolation methods, it will help you to gain more information about the observable value in the range. This will help you to estimate the observable value more accurately.
Thank you.
Okay, great. Let's thank Pei again.